Hello everyone, we're Invaders team. I start by presenting you each member of the team, starting by the team leader Pedro Dente, Emanuel, Gustavo, Ribeiro, Flávio Rosa, and Jorge Benedicto, and I'm Francisca Oliveira. We would like to thank Interred Sugar Program, Easy Business Incubation Center for Portugal, France, Spain, and all the other partners for this amazing experience. It was a pleasure to learn more about space exploration and to gain some work team experience.
After NASA's L-Cross mission, Lunar Crater Observation and Sensing Satellite, it was discovered that there are crystals of water ice on the Moon's poles through better analysis of the hydrogen found in the 90s. The objective of our mission is to photograph the Moon's poles and to identify where exactly there's a bigger amount of water with the help of spectrometers. In the future, when a lunar base is created, it is important to already know a precise location of these crystals. A neutron spectrometer system will measure the total volume present up to 1 meter below the Moon's surface. And the near-infrared volatile spectrometer system will distinguish the hydrogen from water and hydroxy.
Hello, my name is Jorge Benedicto and I will talk and explain the mission analysis. In the mission analysis, we go throughout the mission structure, designing all the mission phases and calculating the delta V budget in each of the mission segments, in order to find out the total delta V value required for the whole mission. In some of the mission phases, no delta V is required, as not orbital maneuvers are performed. However, we left a delta V margin at the end of the mission analysis in order to make orbit corrections and non-planned maneuvers. The whole mission is composed of 7 different phases. The launch is fixed on 16th December to simulate a future mission. In the beginning, the satellite is placed in a GTO orbit by the launcher. As we can see in the GMAT, during the first mission segment, the CubeSat will propagate through the initial orbit to reach the true anomaly of 290 degrees. When the satellite arrives to the desired point, it starts a loop sequence that will take 26 days. The CubeSat uses finite burns to propagate throughout the space. To make the propulsion more efficient, the satellite will perform the finite burns close to the orbit perigee. We can calculate the delta V needed for this loop sequence using the rocket equation and the fuel mass difference in each of the loop orbits. The third mission segment consists on placing the satellite in the optimal location to start a lunar transfer. The propagation does not require the use of thrusters, therefore no delta V is needed in this mission segment. At the beginning of the fourth mission phase, the satellite is at the point with true anomaly of 160 degrees. From this point, we create a target maneuver which will allow the CubeSat to perform a polar flyby in the Moon. Using the GMAT software, we can define the burn time and the velocity values for the 3 directions as variables. In order to make the satellite do a polar flyby, we need to constrain the maneuver with the objective of performing an hyperbolic orbit around the Moon.
Hello, I'm Flávio Rosa and I will explain the second part of the mission analysis. So, our fifth mission phase starts with the first Moon flyby that will have a Moon altitude of about 38 kilometers. This flyby will be used to take pictures from the Moon's south pole, and it is shown in here in blue. As soon as the satellite reaches the periapsis, it will start the insertion burn in dark blue. This maneuver will allow us to achieve an high elliptic orbit around the Moon with its periapsis right above the south pole. After the insertion burn, we'll be able to transmit the data from the first flyby. Afterwards, reaching the orbit's apoapsis, we'll perform a very small burn to adjust periapsis to a height above about 20 kilometers. The second flyby will be closer and on a different location above the south pole, like in here, shown in orange. Following the second flyby, the spacecraft will transmit the data again and remain on the Moon's orbit with a minimal amount of fuel, so it's possible to obtain new data if needed.
Hello, my name is Gustavo Ribeiro, and I'm the responsible of the space propulsion area of the Moon Invaders team. First, we started by doing a thorough research about the CubeSat missions already done and which type of propulsion system they used. One of the main problems we identified was that there aren't almost any chemical propulsion systems launched or being planned for use in CubeSat's missions. This is due to the piggyback launch nature of CubeSats that forbids them to put in risk the main payload of the launcher, and this would automatically exclude the chemical thruster option. However, after consulting a specialist, we decided to underestimate this point. On the other side, the electric thrusters also had a major problem. That is, because of their very tiny thrust force, they require many time to achieve their destiny. In this project, that has a lot of importance because the CubeSat would spend a big fraction of its lifetime orbiting around Earth and crossing the Van Allen radiation belts, which is very harmful to the electronic components if they are not very well protected. After we determined the necessary delta V, we investigated the characteristics of the available thrusters in the market. During this analysis, we always tried to search for a thruster that would be reliable and innovative at the same time. After some discussion, we decided that a chemical thruster BGT-X5 manufactured by Buzek is the one that best suits our needs. The BGT-X5 is a green monopropellant thruster that features a highly stable green propellant that enables a smaller, lighter propellant tank and a lower wet mass. It also reduces transportation costs, ground handling time, and allows for simplified storage due to its lower vapor pressure. The thruster is able to provide 225 seconds of specific impulse and 0.5 newtons of thrust. In total, we will have 6.6 kilograms of propellant.
Hello, my name is Emanuel Castanho and I am in charge of the Attitude Determination and Control and Electric Power Subsystems. This ADCS, also called Guidance, Navigation and Control in the literature, is composed by an integrated unit, Cube IDCS 3-axis, that combines different attitude and navigation components into a single part. It has 3 reaction wheels for full 3-axis control that ensures the point accuracy required of 0.5 degrees. A 4th reaction wheel is used for reduced errors and for desaturation because magnetometers are not useful for attitude control near the Moon. The integrated unit has a module called Cube Computer, which will be used as main onboard computer and storage for the camera data. The electrical power system, or APS, provides, stores, and distributes electrical power to all subsystems. To regulate and control all the APS subsystem, we choose the NanoPower P60. We need a gallium arsenide solar array that can provide 70 watts during daylight for the entire orbit. We choose the custom panel from Pumpkin Space Systems. Each cell provides 1 watt, so to get the 70 watts we need 72 cells to maintain symmetry. We need a lithium-ion battery that can store up to 93.42 watt-hour. The intelligent protected lithium battery from Pumpkin Space Systems is a good option for our project because it can store up to 100 watt-hour.
Hi, it's Pedro again with the mechanical design and structure. A 6U CubeSat of 14 kilograms was selected. All the components represented in orange are fuel tanks. These cover more than half of the satellite. This is expected because a chemical propulsion system was chosen. Chemical propulsion systems require a lot of propellant. Another factor that contributes for the huge amount of fuel needed is the considerable distance from the Earth to the Moon. Here, we have the payload better represented, with a camera and 2 spectrometers. A sliding door will open when the satellite is executing the flyby. During the rest of the mission, this door is closed. Here, in brown, we can see the attitude determination and control subsystem, which is approximately located on the center of gravity of the satellite. so that the reaction wheels perform less effort during maneuvers. Here, the system is better represented with the 3 reaction wheels, one for each main axis. This box, here, is for the command and data handling and works as an onboard computer. Now, about the solar arrays. The panel-mounted approach tracks and points the solar array to get the best sun incidence angle. It has 72 solar cells. Inside the satellite, there are gimbals that fold the solar array in order to join them to the satellite's external structure. The solar arrays also need to be placed away from the payload, as shown here, and other spacecraft subsystems because of the high temperatures of the solar cells. The antenna, where I'm pointing, was placed in the opposite side of the payload so that after the flyby, the antenna is more easily pointed towards the Earth to realize the transmission of the data acquired to the ground station.
Hi, I'm Francisca, and I'm presenting the communication subsystem and ground segment part, followed by the thermal control subsystem. The first subsystem is one of the most important in a satellite, because without it, we can't have information about telemetry or data from the satellite. These communications are known as inter-satellite link. We've chosen an X-band patch antenna, with one of the most powerful band, each around the 8 and 12 GHz frequency, and the transmitter has to be an X-band transmitter as a result of antenna radio frequency. Both of it has an output power of 4 watts. The GPS receiver is a new space system GPS receiver with 12-channel hardware-based receiver which utilizes a well-established GPS chipset, and that chipset has been successfully flown by a number of organizations over many years. This GPS receiver has an output power of 1 watt excluding an active antenna. These GPS applications have accurate determination of orbital position, the knowledge of time, orbit maneuvers and time, and position stamping of payload data. This antenna's transmission speed is 1000 bytes per second, so to transmit the estimated 10 megabytes of data of each flyby, we'll need about 2 hours and 20 minutes. According to GMAT contact located function, each of our contact periods while orbiting the Moon will be around 400 seconds, so each transmission will be done easily after each flyby. Now about thermal control subsystem, we've chosen for the coating the multi-layer isolator, composed by Castanho in surfaces of satellite and Mylar with multiple layers, because it's used to reduce the heat exchanges by radiation between the satellite surfaces and the environment. This coating have low emissivity, 0.02, an effective absorption close to 0.05, and an effective thermal conductivity of 10 to -4 watt per meter Celsius degrees. The Mylar belongs to a specific family of polyesters, and the micronets of nylon covered by Castanho layer produce a highly resistant and dimensionally stable by high temperature action.
The final solution is a 6U CubeSat of 14 kilograms that performs 2 flybys over the Moon's south pole. The payload consists of a camera and 2 spectrometers.
It has 72 solar cells that provide power to the entire mission. The attitude and orbit control subsystem is composed of 3 main reaction wheels plus 1 to ensure that the system remains functional if one of the main reaction wheels fails.
The selected chemical cluster is reliable and innovative at the same time, and allows the mission to be accomplished in less than 40 days.
If required, extra maneuvers can be performed in order to extend the mission time and gather more data of ice water crystals, or fulfill new objectives using either the camera or the spectrometers.
The preliminary design gave us the path we must follow regarding the satellite mission. As we keep on adjusting and making deeper analysis for the whole satellite design and mission phases, the Moon Invaders satellite changes as well. Therefore, the iterative process must go on to optimize the final solution.
We really enjoyed to work on Nanostar project, and I hope you like this presentation. Thank you for your attention.